So in this lecture, we'll continue with the dislocation. Specifically, we are going to discuss on the dislocation motion. Uh, so the first point you see, already we have discussed in the last lecture also, that Burger's vector of a dislocation is invariant. At all locations along the dislocation, the Burger vector is same. You have seen that if there is a mixed dislocation like this, suppose within a crystal, a mixed dislocation is like this, and you know that we can define dislocation line vector as tangent at different location. I am showing the dislocation line vectors. As you can see, these are the dislocation line vectors at different locations. It is basically the tangent to the dislocation line. And but the Burger vector, so the dislocation line vector, as you can see, is different at different location along the dislocation line. But the Burger's vector is same everywhere in that dislocation line. The dislocation line that is created because of certain slip, that Burger's vector is same throughout anywhere. That means the Burger vector at this location is this. Burger's vector at this location is this. So here also the Burger's vector is this, and here the Burger's vector is this. That means throughout the dislocation line everywhere, the Burger's vector remains same. That is the first point. Okay. So Burger's vector of a dislocation is invariant at all locations along the dislocation. The Burger vector is same. Okay. Now coming to the next point. That is the vector sum of the Burger's vector of dislocations meeting at a point is 0. That point is called node. That means if you consider a crystal, let us consider this is one Burger vector. This is one dislocation, and let us consider there is another dislocation. Suppose this one is another dislocation, and green one is another dislocation. Suppose this one is another dislocation. So now these three dislocations, as you can see, is meeting at this point. Okay, so this particular point is called node. Okay, where all these dislocations can meet. So according to this statement, that vector sum of the Burger's vector of the dislocations meeting at the node is 0. So this particular dislocation indicated by the blue line may be having a Burger's vector, say B1. Maybe this one having some Burger's vector, say B2. And this one may have some Burger vector, say B3. Let us consider, say, this is B2, such that if they are meeting at a node, three dislocations line, if they meet at a node, then remember the summation of these three Burger's vectors, that is B1 plus B2 plus B3, this summation must be equal to 0. This is what is the statement. Okay, so summation of the Burger's vector of a dislocation meeting at a point is 0. So this is what is the second point. The third point is very important. A dislocation line cannot end abruptly in a crystal. Okay, either they meet in a node, as you can see in this example, one dislocation line shown by the blue, it is ending at the node, or the green dislocation line is ending at the node. So they can end at a node. They cannot end abruptly within the crystal. That means suppose this is a crystal and one dislocation line suddenly cannot end within the crystal. Okay, either they can end at a node, that is the first point, or they end at the surface. So if you consider the whole volume, in that case, the dislocation line can end at the surface. Okay, or closes on itself as a loop, or closes on itself as a loop means, if you consider this is a slip plane, say, so this line, as you can see, this is a loop, maybe a dislocation line, so that it divide the slip plane into two part. One is slipped part, another one is unslipped part. And the uh, this is basically the boundary between the slipped part and the unslipped part. What is the dislocation? So either they end at the surface, or they end at the node, or dislocation can be a loop, so that it divide the slip plane as uh, slipped and the unslipped part. So these are the only ways. They cannot abrupt suddenly within a crystal. Sorry. Okay. So next we'll see the elastic strain energy associated with the dislocation. Okay, as you know that dislocation is a crystal defect, so definitely it is associated with the strain energy. Already we have seen that in case of edge dislocation, compressive and the tensile strain energy is there around the dislocation line. Similarly, in case of um, screw dislocation, it is the shear strain energy. And in case of mixed dislocation, it is the general state of strain energy that is surrounded uh, the dislocation line. So if we want to measure the strain energy, this is the approximate measurement of the strain energy which is used. That is the uh, elastic strain energy per unit length of the dislocation line. Okay, so E here is the elastic strain energy per unit length of the dislocation line, and this is given by the formula. You can see half G into B square, where G is the shear modulus of the crystal material and B is the magnitude of the Berger's vector. Okay, so as you already know, this is an approximate result. This is an approximate result, but this is commonly used to estimate the strain energy associated with the dislocation line. I'm just giving you an idea so that you can understand that this will be of the similar order of magnitude. You see that what you know about the strain energy. Already you know that strain energy per unit volume, this quantity, strain energy, elastic strain energy per unit volume, this particular quantity, you know that half into stress into strain, right? Half into stress into strain. This already you know, per unit volume, this is what is the strain energy. So what is the strain energy? To find out the strain energy, you have to multiply this quantity by the volume. So the strain energy is equal to strain energy is equal to half into stress into strain into volume. Okay, so now if we consider the length dimension as L, so volume is of the order of L cube. Okay, and you already know that within elastic limit, stress and strain are related by uh, Hooke's law. So if you write that stress is equal to some modulus of elasticity, okay, multiplied by strain. In case of normal stress, it is the Young's modulus. If it is a shear stress, it is the shear modulus. So basically here, this expression, if you want to see that, it is expressed actually in terms of shear modulus. Okay, so shear stress, you know that shear modulus into shear strain. If we call that shear strain to be theta, or you can call shear stress to be gamma. So whatever the symbol you used. So this is what is the relation between shear stress and shear strain. So you just simply replace this quantity, because half into stress into strain in terms of shear strain energy, if you write, that will be half into shear stress into strain. Okay, and if you simply write this quantity multiplied by volume, and it will become half into g into nu square, because if you replace this shear stress by this quantity g into shear strain, so there is already one shear strain, so it will be g into shear strain square into volume, and volume is in the order of say L cube. Okay, so this is the kind of expression of you get for the strain energy. And if you try to get some estimation of the uh, gamma is basically the shear strain. If you remember how we measure the shear strain, if you give a shear force, uh, so it will deflect by some angle, and that angle is a measurement of the shear strain. Since the angle is very small, so tan of that angle is same as that angle. So if this is the small displacement it occurs, this is basically the kind of amount of slip that occurs with respect to this, and this is what is the dimension of the crystal in that order, so that is L. Okay, so this gamma is in the order of basically B by L. Okay, so if you simply put the value of the shear strain here in this expression, it will come that half into G into in the order of B square divided by L square into L cube. Okay, so you can see that this expression will simplify. L cube by L square is L. So basically the expression becomes the strain energy is equal to half G B square into L. So per unit length, if you want to find out, so basically the strain energy uh, per unit length, strain energy per unit length, if you divide this by L, then it is in the order of half GB square. So this is just an giving you an idea that where from this has been established. But this is the approximate result, even if it is a tensile stress and tensile strain in case of edge dislocation, still we use the same formula to find out the strain energy associated with the dislocation. It is not that only in case of screw dislocation you use this formula, because in screw dislocation only pure shear is there. In mixed dislocation, in edge dislocation, everywhere this is the approximate result which is used for even if it is a pure tensile normal stress. Okay, so this is the standard practice of expressing the energy associated with the dislocation. Now coming to the dislocation, as you can see that dislocation, you know that slip of the atom. So amount of atomic movement, if you remember that how we have created dislocation by showing you as if virtually we are pushing one part of the crystal with respect to the other part. So in that case, you can understand that slip will be definitely in a direction where the distance between the atom is the smallest. Okay, so slip always be in a direction where the distance between the atoms are closest, and definitely the closest direction, closest atomic direction means where towards the neighboring atoms. So the atoms which are in contact basically. Okay, so in BCC crystal, if you see which are the closest atom, you know the along the diagonal, right? Along the diagonal, atoms are the closest. In case of FCC crystal, you know that along the phase diagonal. In case of BCC, along the body diagonal. In case of FCC, it is along the phase diagonal. In case of simple cubic crystal, you know it is along the edge. Okay, the atoms are closest. So definitely the Vargas vector will be also in that direction. And what is the Miller indices of that family of lines? You know that in case of BCC, the body diagonal, the family of lines are indicated by 111. This is what is the Miller indices under caret. Okay, so under this family, any direction can be considered. And what is its, if you just multiplied it with the magnitude, you know that this one basically indicate what this unit length indicates in terms of lattice parameter is A. In case of cubic crystal, it is A is same in all directions. So that is why A, and divided by 2, because it is basically distance from one atom to another atom. This is the smallest distance that is to be traveled. That is why the Burgers vector in case of BCC is A by 2 in the direction 1, 1, 1 family. Clear? Similarly, in case of FCC, you can see along the phase diagonal. So that is why you can see the 110 family, any one of the phase diagonal direction, and the closest distance definitely will be A by 2. This part is clear to everyone?
Yes, sir.
Okay. So this is dislocation, magnitude and direction, how we fix for different types of crystals. Now, certain important properties of dislocation. The first, here you see these two properties, that opposite dislocations lying on a slip plane attract each other and may annihilate each other if brought close enough. Specifically, it has been shown for the edge dislocation, as you can see here, that in this diagram, let us consider the bottom diagram, this diagram. Okay, so in this diagram, you see that this particular thing is showing the strain field of a dislocation, edge dislocation. As you can see from the symbol, it is the positive edge dislocation that has been shown in here. And you see that in case of positive edge dislocation, at the top part, that means in this region shown by the green, is under compression, whereas the yellow part is actually under tension. Okay, now let us consider on the same slip plane. Here you can see this is suppose the slip plane in the crystal. Maybe a few distance away there is another edge dislocation on the same slip plane. Okay, and but here you see the edge dislocation type is not positive edge dislocation but a negative edge dislocation. So here is a negative edge dislocation. So that is why the tensile strain energy that is in the top part, whereas the compressive strain energy which is at the bottom part. Now definitely if they come close, in that case there will be a tendency that they will merge one another and they will form a perfect crystal, because here there is some compression, here there is some tension. So ultimately they will cancel, or the whole dislocation will annihilate if they merge. So in this way they will attract each other, because that will be energetically favorable. Okay, I think this part is quite obvious. You can understand what will happen if a positive dislocation, edge dislocation, and the negative edge dislocation lying on a same slip plane, they attract each other. Okay, and ultimately they annihilate the dislocation, and it is behaving at that part as a perfect crystal. On the other hand, the second part, if the dislocations of the same sign lying on a slip plane, they will repel each other. Let us consider the situation is that two dislocations, both are positive dislocations, or it can be possible for both are negative. So if they are of the same sign, that means this one is positive dislocation, this one is also positive dislocation, then they definitely will repel each other. They will not try to come closer to each other. Why? We can easily show this particular phenomena with the help of the we have seen the expression for the energy per unit length that is associated with the dislocation is half into g into b square. This expression we have seen. Now let us consider if these two dislocations stays separately. That means these two dislocations stay separately. In that case, what is the total amount of energy associated here? So we can write in that case, this E will be a summation of the energy associated with 1 and 2. Let us consider this is 1 and this is 2. So what is that total energy? So half into G, that will be common. And Let us consider B is the amount of slip here. So both having the same. So B square plus here also B. So this is the total amount of energy that will be associated. Now, if they come close and if they merge over another, in that case, what will happen? In that case, definitely it will show a dislocation of uh, Burgers vector is 2b if they come closer, right? Because here is 1b, this is of the similar size, so they will be of 2b. So if they come close, in that case, it will be of size 2b. So corresponding to size 2b, what is the energy associated? So energy associated, if they merge, in that case, will be half into g into 2b whole square. And it is quite clear from this expression, it is coming 2 into g into b square. So what you can see, the energy associated if they merge is more than the energy associated if they do not merge. So definitely energetically favorable situation is that they will not merge, because every crystal always will try to keep its energy minimum, right? So they will repel each other, they will not merge, they will repel each other, so that is the energetically favorable condition. Clear? Now coming to this particular slide, where we'll see that the dislocation, interaction of the dislocation with the point defects. So here in the crystal, you can see this is an example of a positive edge dislocation that is taking place near this region. And here this region is under compression. As you can see, the atoms are very closely spaced, whereas this region is under tension because the distance between the atoms are quite large with comparison to the normal atomic distance. So this particular region where this kind of edge dislocation is there, we can see different kinds of point defects, like interstitial point defects. Already you know that interstitial point defects is what? That some external impurity atom can go into the interstitial void space, right? Now, if you see, since due to this kind of line defect, definitely in the tensile region, if you look at this tensile region, you see that the interstitial void space is quite large. Since the interstitial void space is quite large, so there is a chance of interstitial atoms will come in this region. Okay, so this is the thing that we can observe. Next, we see the substitutional smaller atoms. Okay, so substitutional smaller atoms, you know already that some of the parent atoms can be replaced by the substitutional atoms in case of substitutional solid solution. And in that case, the size of the solute can be either larger or smaller than the parent atom. So here, if you observe in this region where the atoms are under compression, so definitely these atoms, if we are talking about the substitution of this atom may be substituted by a smaller atom. So in that case, energetically, this will be favorable, because already because of the large size atom, parent atom, it is already under compression. So some amount of compression will be released if some smaller atoms substitute the atoms closer to this region. So that will be energetically favorable. Okay. So similarly, the larger atom, if you observe substitution larger atom, so definitely larger atom can be substituted this region where the tensile, that means the atoms having very large distance among them. So that region atoms can be substituted by the larger atoms. Okay, that will be energetically favorable. Now the vacancy also can be created in this region because you can see these are the regions where maybe from other places some atom can go into this region and it can create some vacant space somewhere else, because these are the regions where the distance between the atoms are quite large. Maybe some other atoms from the uh, pure crystal where the crystal is perfect may go there, and that will create a vacuum. That chances are also there. Now you'll see the density of dislocation in a crystal. So this is very important to get an idea about the density of dislocation. So total length of dislocation line per unit volume of the crystal is a kind of measurement of the density of dislocation. So we know that dislocation is the line defect. So what is the total length of line that is defective? Okay, so per unit volume of the crystal, that is the measure of the density of dislocation. And what is the unit? The meter of dislocation line divided by the volume of the crystal. This is what is the unit. So for example, you just to get an idea that in a well annealed crystal means the crystal is heated so that the different kinds of point defects and other non-equilibrium defects probably will gone from the crystal. Already you know that dislocation line defect dislocations are not in thermodynamically stable equilibrium. So that is why if you anneal them, if you heat them, it is expected that most of the dislocation will get out of the crystal and it will be free of that. But actually this is not so. Even if the in the annealed crystal, that means the well treated, well heat treated crystal, you will find that the dislocation density is in the order of 10 to the power 8 to 10 to the power 10 meter per meter cube. So you can understand that a uh, huge length that is defects. Okay, so huge defective lengths are still present even if it is well annealed. Now you'll see the slip or glide motion of a dislocation. Now, motion of a dislocation on a plane containing B and T. Okay, so dislocation, it is not a static. This is a static line that we have seen that around which some defect is there within the crystal, but this line can move under some external maybe mechanical energy or some thermal energy that is applied. It is possible that dislocation line can move. Okay, so the motion of dislocation takes place in the plane containing B and T. Already you know T is the dislocation line vector and B is the Burgers vector. If you remember simple example of the slip plane, uh, if you remember, this was the uh, F and E on the slip plane. Okay, so if we consider this is what is the T, and if we consider this is the B, so this plane is what is the slip plane. Okay, so this is the slip plane, the plane containing B and T. This is what is the slip plane. So motion of dislocation takes place in the slip plane. That is the first point. So what is slip plane? It is the plane containing B and T. So if it is the plane containing B and T, then it is clear that in case of edge dislocation, you know that this T and B are perpendicular to each other. In case of edge dislocation, either they are 90-degree or 270-degree, but they are perpendicular to each other. In case of screw dislocation, if you remember, B and T are along the same line. Either they are angle between them is 0 or is 180-degree, but they are in the same uh, line. That means what is the plane containing B and T then? In case of edge dislocation, a unique plane you can define with B and T, because two intersecting line will generate a plane, so that you can understand, okay, this is the plane over which the dislocation can move. But in case of screw dislocation, you can understand through this B and T, since it will form a line, then you can actually draw infinite number of planes through that line. Okay, so through a single line, actually you can draw infinite number of planes. So you can draw this plane, you can draw other planes, all are containing this line. So you can draw infinite number of planes through B and T. So in case of screw dislocation, you have to understand the slip plane is not uniquely defined. But in case of edge dislocation, definitely slip plane is uniquely defined. In case of mixed dislocation, you know that mixed dislocation, the angle between B and T is not 90 degree, or they are not aligned. So in that case also, you can uniquely define the slip plane. Okay, but so in case of edge dislocation or mixed dislocation, slip plane is uniquely defined. In case of screw dislocation, uh, any plane that is passing through B and T is a slip plane. You can consider that to be a slip plane. Okay, so next thing is that the direction of motion is always perpendicular to T. Direction of which motion? Direction of the dislocation motion. So dislocation line will move in which direction? Dislocation line will move in a direction always perpendicular to T. Dislocation line will move perpendicular to T. That means in case of edge dislocation, if we try to remember, if this is the dislocation line fe is the dislocation line, so this is what is the dislocation line vector. So remember, so this line will move perpendicular to direction of T. So this is the direction of T, so motion will be perpendicular to that. Always this is the thing you have to remember. So it will always be perpendicular to that. In case of mixed dislocation, if you consider this is the mixed dislocation line, that means T at different point you can define by the tangent. In that case, how the dislocation line will move? Dislocation line will move perpendicular to that. That means in this way dislocation line will move. That means it will move in that direction. So always it will move perpendicular to that. So this is what is the second point, that the direction of motion of the dislocation is always perpendicular to T. Third point is the slip plane is uniquely defined for edge and mixed dislocation, but is not so for the screw dislocation that we have already described. Now let us try to visualize the slip motion of edge dislocation. Okay. So here in this crystal, you can see the location of the edge dislocation. So here you can see this is the location of the edge dislocation. As you can see, this is the part plane. Lower half is not there. So this is the position of dislocation. And this is like the point F, right? This is like the point F. And where is E? E is actually there. If you draw, if you just think perpendicular to this plane. Now, dislocation line, this line, that means the FE line, that means the dislocation line vector, edge dislocation line vector. So that motion of that is the motion of dislocation. So motion of dislocation will be perpendicular to that line T. So it will, that means that line will move in this direction. This is what is the idea, that EF line will move in this direction. So let us try to visualize that how it will move. Observe carefully. So this is the initial position. Now see the second step. As you can see that it has moved from, previously it was here and now it has moved to this location, right? Then you see that it has moved to this location. You see this has moved to this location, and finally you see it is getting out of the crystal. So let us see again. So if we start from here, try to visualize the motion of the dislocation. So when the dislocation will get out of the crystal, that means dislocation motion started and finally it is getting out of the crystal. And when the dislocation motion getting out of the crystal completely, it goes to the surface and getting out of the crystal, you see that the whole crystal having a permanent deformation has taken place. A permanent deformation has taken place. This is what is, remember, the plastic deformation. This is irrecoverable. This is irreversible process. Okay, you cannot, because some thermal energy that is lost cannot be recovered. So this is an irreversible process. This is a plastic deformation that takes place, and that means what we can see is that the plastic deformation in the material takes place because of the motion of the dislocation. That is the most important thing that we can uh, identify here. So see it again. So here some defect is there in the form of dislocation, edge dislocation, and when the dislocation get out of the crystal, plastic deformation takes place. Plastic deformation means permanent deformation. This is not elastic deformation. Elastic deformation kind of reversible process. Okay, if you withdraw the force, it will again come back to its position. But this is a plastic deformation. It's a permanent deformation. It is irreversible. Okay. Next, see, try to visualize the slip motion of screw dislocation. We have seen the slip motion of the edge dislocation. Now we'll see the slip motion of the screw dislocation. So here you can see the crystal where this is the line. Just try to visualize which is the dislocation line. This is H and this is a G. Okay, and around which basically the shear strain energy is associated. And you know that if this is the direction T, then the motion of the dislocation line will be perpendicular to T. So motion will be in that direction. So slip motion will be in that direction. Okay. So let us see. It's try to visualize its movement. Follow carefully. Previously the line was here, and now it has moved to this location. So gradually the line is moving in that direction. Okay. And then you see, and finally when that dislocation line moves out of the crystal, again you see the permanent deformation has taken place. Okay, so this is what is the slip motion of the screw dislocation. Okay, now try to visualize the slip motion of mixed dislocation. So it's very difficult to visualize the mixed dislocation. Here basically the screw part you can understand, and here this is basically the actually these lines are very faint, so difficult to. So actually here is the edge dislocation you can see. So this is basically the mixed dislocation line. Okay, so as the slip motion started, so this particular line, this dislocation line will move in a direction perpendicular to the dislocation line vector. That means it will actually move from here to here, it will move from here to here. So what you will observe in the crystal is that this edge dislocation is gradually shifting in this direction, and at this point you will find that the screw dislocation is shifting, and on all the inner mixed points you will find that gradually are moving in that direction. So this is the way by which the whole dislocation motion will take place. So if you just observe, it's very difficult to see that part, I know. And here you can see that it has now come to this end almost here. This is the part plane here. And you see that finally the permanent deformation has taken place. Okay, so this is the way the dislocation line, whether it is a straight line or it is a curved line, that moves. And why they moves because of either mechanical forces, maybe this mechanical forces given by some hammer or something else, the external mechanical force we can give. Because of that this can happen. You know how we do the plastic deformation, we apply forces, okay, and then it is possible to change the shape of the material. So when we are changing the shape of the material, when we are making the permanent deformation in the material, basically we are giving the external mechanical force or the thermal energy. When we are doing all these things, basically we are giving some energy so that the dislocation line can move within the material. So we have seen the slip motion of the different types of dislocations. Now we'll see the climb motion. Okay, so the climb motion is a motion of the edge dislocation on a plane perpendicular to the slip plane. Okay, uh, this is also a very important motion because this is very common that sometimes it is fine that here you can see in this example in the figure, you see there is a positive dislocation. This is the position of the dislocation, as you can see. Now suppose this red line indicates the slip plane. Okay, so it is during the motion what is happen, that this particular dislocation line is gradually moving in this direction. Gradually, this is what is the slip motion. Then when it will come this location, you find some second phase particle, maybe some impurity particle or something is there. Because of that, some high strain field is generated at this region, and because of this strain field, then this motion of the dislocation over the slip plane will be difficult, because a high strain field will restrict the motion of the dislocation. But dislocation always try to get out of the crystal, try to go to the surface. So to avoid this slip plane, because this slip plane is interrupted by this second phase particle maybe. So in that case, what happens, it is possible that here the part plane is there, then it is possible that somehow this part plane will lose some set of atoms. Let us consider this set of atoms. Here in this diagram you can see this is single atom, but actually if you think of the whole crystal, it is basically a set of atoms which are there, right? If you visualize the basic figure that with which we have given the examples, so what you will find is that this set of atoms perpendicular to the slide you just think of. So if this set of atoms somehow go to some vacant place, you know that there are different vacancies present within the crystal. So if some of the atom goes to some vacant place, suppose this region is a vacant region, some vacancy is there, suppose here is some vacancy. So this set of atoms, if they go to some vacant positions, similarly this set of atoms can go to some vacant places in different locations. So in that way, what is possible that this part plane will shrink. So this part plane will now contain these sets. This will no longer be there. Okay, so you can understand that in this way it is possible to lose these atoms to some vacant places, and the part plane now shrink, and part plane becomes like this. So when part plane is this one, then the position of dislocation is now this location, because this is now the part plane. So here is the position of dislocation. So the new slip plane will be this one. So now what actually happened in this way, that the slip plane actually moves from this location to some higher position. And in this way, now it can again continue its motion in this slip plane. And in this way, it can avoid this obstacle in its path. Okay, and the dislocation can get out of the crystal. Okay, so this is the process by which ultimately what happens, that this dislocation line actually moves up. Actually, it moves up means it moves perpendicular to the slip plane. That is why this is called the climb up motion, okay, or the positive climb motion. Okay, so in this way, a dislocation motion is also possible, and that motion is called the climb motion. Exactly in a similar way, one can think in that way also, that some atoms from other places, some atom from other places can also come in this region, and in this region where there are basically the part plane is there. That means suppose this is the part plane, and below which the planes are missing, maybe below which the planes are missing, this is the part plane. So from from other atoms from the crystal, it is possible that this part plane can extend. So in this way, it is also possible. So in this way, instead of shrinking the part plane, it is possible that the part plane can extend, and the new slip plane becomes this one. And in this way also it can avoid the obstacle. Okay, either by shrinking the part plane or by extending the part plane. So in one case, either it will create the new vacancies, like when it is extending, or it will annihilate some of the vacancies. That is the shrinking process. So in this way, also the climb motion are possible. So one case it is called the climb up motion, another one it is called the climb down motion, or climb positive climb or a negative climb. So this is the basic idea. But one thing you have to remember, if you just want to compare with respect to the slip motion, remember that the slip motion is a conservative motion. That means the volume is not going to change because of the slip motion, only the shape is changing. But in case of climb motion, remember this is not a conservative one. Okay, because when the vacancies are created, like in case of climb down motion, when the vacancies are created, in that case, remember the volume actually increases. On the other hand, when the vacancies are annihilated, like when the part plane is shrinking or the climb up motion, in that case, remember the volume is decreasing. Okay, so this is, in that way it is not a conservative. That is the difference that you have to remember. Okay. So this is brought here. Those things are actually written. You see, the second point, it causes the incomplete plane to either shrink or expand. And this is brought about by subtracting or adding rows of atoms to the edge of the part plane. So in that way, either they extend or they shrink the part plane and changes the slip plane so that they can avoid some obstacles in its path, maybe. So here, another good visualization, you can see here is the part plane, and you see that in case of positive climb means you can see that here you can see the positive climb motion where this particular atom goes somewhere else, and ultimately the part plane shrinks. So in this way, this is the positive climb motion or the climb up motion. Okay, so dislocation due to vacancy annihilation. Okay, so for that, what is required? This atom definitely will go to some vacant location. It will go to some vacant location, and in that way, the vacancy will be annihilated to shrink the part plane. On the other hand, you can see that maybe for the climb down motion, some other place, some vacancy will be created and the atom will be added. As you can see, somewhere some vacancy is created and the atom is added. Okay, in this way, the part plane extended. Okay, this is the negative climb or the climb down motion. Okay, so you can see that climb motion is non-conservative. Volume is either increases. When the volume increases, when the vacancy will be created, and when the volume decreases, this is the case when the volume decreases, when the vacancy uh, uh, will be annihilated. Now coming to this cross slip motion, which is observed in screw dislocation. As you know that in case of screw dislocation, slip plane is not unique. But slip motion, you can think, let us consider, as you can see that, suppose this is the direction of B, Burger's vector, and let us consider that this is the T. Let us consider in case of, slip motion, B and T are either in the same direction or opposite. So maybe this is the T. So in which direction the slip motion will take place? So the slip motion will take place always perpendicular to T. So slip motion will take place in this direction. That is clear because B and T are in the same direction. So slip motion is taking place in that direction. Now suddenly, suppose because of some reason at this location, when the T at this location, when the dislocation line is at this location, some obstacle comes. Okay, so in that case, where if some obstacle is coming in this path, then it is difficult to continue to move in that path. So what happens in this case? in case of a screw dislocation, it simply changes its plane from this plane to this plane, as you can see. It changes from plane this plane to this plane, because that plane is also a slip plane, because you know that any plane drawing through B and T are basically the slip plane, and you know that we can draw infinite number of planes. So just to avoid the obstacle, it just moves in this direction, provided it is in the same family of plane in which it is moving. So if the sufficient amount of external mechanical energy is available, so that the component of the force that is sufficient to move the dislocation, if that is available, then it will follow moving in that direction also, because that is also a slip plane. Okay, so this is the thing that happens, and this is called the cross slip motion, because in case of screw dislocation, there is no unique slip plane, so it just try to move at a particular angle, and that plane we can also think of a slip plane, because through B and T you can draw many slip planes. And if provided, if the energy that is available for the movement of the screw dislocation, the component in that direction, if that is available, if that is sufficient, then it will continue to move in that direction. Okay, here in this diagram, obviously it has been shown again another slip motion. So it's a double slip. So for first slip, cross slip here has been shown, then second stage of cross slip, and then further it can continue in that direction. That is also possible. Okay, so this is the cross slip motion, that is only happens in case of screw dislocation, where there is no unique slip plane. Okay, so that in this way we conclude the dislocation and its motion, and in the next lecture we'll start the surface defects. Thank you. Wait.